Welcome to the presentation of Group 51 Simulation Project completed in partial fulfillment of the BUY 321 module for 2018. With Koi being a well-renowned modern contemporary Asian cuisine restaurant situated comfortably towards the fine dining end of the spectrum, maintaining an impeccable reputation is absolutely paramount. Koi is further pressurized by the extent of competition it is surrounded by in the Menlyn Main precinct, with the urgency to retain customer loyalty and create an unforgettable customer experience for newcomers when the Sun Arena at Times Square attracts hundreds of consumers to the precinct with popular shows and events. Currently, Koi experiences major constraints in retaining a good level of customer service due to its kitchen being unable to handle the influx of orders on busy evenings, resulting in painstakingly long waiting times, resulting in disgruntled customers who have lost their patience and confidence in the restaurant's ability to provide them with a seamless dining experience. With the above mentioned in mind, and due to the urgency to rectify this inefficiency, this led to the development of the core competency of the group simulation to identify where the root cause lay with respect to the kitchen's inefficiency, and thereafter evaluate how such a problem could be rectified by virtually testing realistic alternatives. Simulation modeling as a decision support tool provides Koi with a multitude of techniques to investigate alternatives rigorously without the restaurant experiencing any downtime, giving rise to the possibility of maturing improvements of interest thoroughly before implementing to ensure as little impact on the customer base as possible that could result in further reputation damage of the establishment if such improvements have not been fully matured before implementation. Since the root cause of the main kitchen's inefficiencies leaves a lot of room for interpretation, through simulation the group could better visualize where the root cause lay to promptly develop effective and practical solutions to rectify the constraint on a small scale. The model also provides a visually aesthetic environment that is easily understood by both the management and chef to better communicate and elaborate on the importance of addressing the problem by timeously implementing the investigating solution. With such a complex problem at hand, a rigorous methodology was required to develop understanding of the main kitchen's processes, layout, equipment capabilities, etc., to develop the problem scope and effectively identify a realistic solution for Koi. The group thus chose to follow the following methodology to ensure accuracy of documentation and the development of a repeatable model. Site visits. These were used to better understand the layout of the kitchen to ensure accurate representation when constructing the simulation layout. Koi management was consulted to retrieve historical data of one of their busiest evenings of 2018 in the form of receipts, which were analyzed to formulate an appropriate rate for the simulation model in terms of order arrivals. Due to the need for data validation to ensure accuracy of our model, time studies were conducted to evaluate the correlation between the model's behavior to what was being experienced in real time by the restaurant. The chef was also consulted to segment the menu items into the 3 processing areas, namely frying, grilling, and dessert preparation, to accurately develop probabilities that were then translated to the model for order item distribution. Capacities and average processing times of the kitchen's equipment was also gathered and inputted into the model. For verification that the simulation layout was accurate, the flow was moderated by the chef to ensure that a representative model was produced. Expert concerns on where the problems may lie and what suggestions are recommended were also sought. Keeping the essence of the problem in mind, a large-scale experiment was performed to simulate and evaluate the main kitchen's overall performance by using the rates derived from the historical data as input. It was identified that it was indeed the frying area that was constrained the most during the peak period of the simulated evening. This area yielded lengthy queues with the corresponding queuing time growing substantially as more orders arrived, clearly showing that it embodied the root cause of the kitchen's inefficiency and inability to process customer orders punctually. Thereafter, it was decided to investigate the frying area more closely to identify what aspect of the area was the main contributor to the constraint. To do this, a small-scale experiment was performed and queues segmented according to the frying technique available, namely deep frying and wok frying. Deep frying represents two compartments to replicate the deep fry compartments available, with one compartment solely dedicated to duck, which can be seen in the model. After running the simulation and graphing the segmented queuing, it was identified that the single compartment dedicated for all other deep frying was insufficient to accommodate the extensive order influx, and hence a parameter was formulated to test whether the addition of another deep fry would rectify the problem sufficiently, reducing queuing time and queuing buildup drastically in the frying area. To ensure accurate interfacing with the model, the parameter was represented in the form of a slider, allowing for the user of the simulation to change it easily and monitor the corresponding results when running the model. The above mentioned extends the accessibility of the model to a wide range of audience, irrespective of technological competency. When running the simulation, visually aesthetic graphs are used to depict the most important experimental data that the user can track simultaneously whilst the model runs and immediately reach a conclusion on where the problem area lies and how the parameters alteration can yield a promising improvement for the restaurant. When compiling our results, the as-is scenario as well as the improved scenario were taken into consideration. First, the as-is scenario was selected with a selected capacity of 1, yielding the following results. Throughout the duration of the simulation, an average queuing time in minutes of 39.27 minutes was realized, with a maximum or peak queuing time being at 82 minutes. Then, when considering the improved scenario, the selected capacity was then altered to a capacity of 3 and the model was rerun. With the improvement put in place, a new improved average and optimized average of 4.08 minutes of average queuing time was realized, with a maximum peak of 12.25 minutes of queuing time experienced. Due to one of the group members being employed at Koi part-time, continuous discussions have taken place throughout the development of the model between the group and industry partner with respect to progress, results, and recommended improvements that the model yielded as prosperous yet realistic. The industry partner was very intrigued by what the model had to offer in terms of capability and ease to visualize how an additional deep fry would impact the overall efficiency of the kitchen, and wishes to present the model and findings to management for consideration of the improvement implementation. To retain engineering professionalism, it is very important to understand what this model can and cannot answer. In terms of capability, the model can effectively be adjusted to simulate any evening that Koi wishes to evaluate, over and above the evening chosen. The model can output the corresponding queuing times specific to the frying area, as well as queue counts for the other sections for reference purposes as well. The model effortlessly depicts how the addition of a deep fryer to the kitchen will impact the queuing of orders directly, which can be seen both quantitatively and visually on the model. Limitations in the model exist with respect to not being able to evaluate how a change in the kitchen's layout will impact the kitchen's efficiency, but due to this improvement requiring a lot of downtime to implement, it was decided mutually between the group and industry partner to not be evaluated. The model is unable to replicate the waitering service to customers after orders are dispatched, as this would have yielded too broad of a scope for the model. Throughout the development of the model, Koi was consulted on multiple occasions for valuable insight and constructive criticism. After creating the baseline model, the chef identified that the queuing time was slightly inaccurate for the deep frying segment, as the model still reflected a substantial amount of queuing towards the end of the model. The delay distribution that was used to represent processing of orders was evaluated and altered accordingly to yield a realistic and more accurate representation of the queuing at the kitchen throughout the duration of the simulation. In conclusion, through intimate collaboration between the group and Khoi Minh Main throughout development, a model was produced that was realistic, informative, and concise, yet effective in addressing the problem at hand that Khoi was facing, as well as depicting how Khoi could rectify the problem with meaningful, effective, and minimal downtime improvements that could be visually represented to fully grasp the magnitude of benefit such an improvement would be accompanied by. Thank you.